next talk is on how hard is robust mean estimation by Sam Hopkins.
Yeah, this is great. Thanks, Arvindan. Thanks, Arvindan. This talk is about robust mean estimation, which is the following problem that's received a lot of attention in the last couple of years. Some independent samples, x1 through xn, are sampled from some distribution capital D that lives in Rd. Think of little d as being large, going to infinity. You will get to see these samples, but only after they've been handed to a malicious adversary. The adversary gets to look at all of the samples, select any epsilon fraction of them, replace those by any samples they want, and hand you the epsilon corrupted samples. Your goal is to estimate the mean of the underlying distribution D from these epsilon corrupted samples. And this is the simplest among a number of high-dimensional robust statistics problems which have attracted a great deal of attention in recent years. Robust mean estimation, robust covariance estimation, robust regression, robust clustering, and many more. So recent progress on robust mean estimation and other robust statistics problems has usually taken the following form. So before around 2016, the typical situation was that polynomial time algorithms for robust statistics problems achieved suboptimal error rates with respect to the ambient dimension D. Right? So usually they achieved errors that depended on both the fraction of corrupted samples and the ambient dimension. Think of these are algorithms that are very naive, like throw out the largest samples. Okay? On the other hand, computationally intractable estimators were known to achieve error rates that depended only on the fraction of corrupted samples, removing the dimension dependence. And in 2016, actually from 2016 till now, we've seen progress on a number of problems which has basically removed the dimension dependence suffered by polynomial time algorithms. And all of this is under reasonable assumptions on the underlying distribution D. Some assumption is necessary, and people use assumptions like Gaussianness, which is kind of strong, or that the distribution has bounded covariance, which is kind of weak, or this thing called resilience, which I'll talk about in a second. So this means that we pretty much believe that for most of these problems, you can remove the dimension dependence from polynomial time, from the error rates of polynomial time algorithms. And now the question is, for this talk, what is the smallest epsilon dependence that is achievable in polynomial time? Okay. So of course, this isn't quite well specified, so let's get a little bit more concrete. Let me fix a particular setting to start with. So we're going to fix the assumption that the covariance of the distribution D is identity, or is it most identity, excuse me. And then it's known by an ICML paper from a couple of years ago that you can find an estimator mu hat of the mean such that the error, but the L2 distance from mu to mu hat is at most order root epsilon in polynomial time. Okay? So in the setting of bounded covariance, this is actually information theoretically optimal up to constants. And so you might ask, are there stronger assumptions that you can make which would enable you to beat this root epsilon? Can you get epsilon or epsilon to the 0.99, something going to 0 faster than square root epsilon? And indeed, there are some natural assumptions that would allow you to do this. So one such assumption I'm going to call bounded moments in this talk. If for some integer t you assume that in every direction v, the tth moment of this distribution projected in direction v is order 1, then it's more or less a folklore result that you can get error information theoretically, you can get error order epsilon to the 1 minus 1 over t. So as t gets big, this is going to epsilon. Another assumption you could take, which is a bit weaker, is called sigma epsilon resilience. It has the following flavor. It's a stability under removing a tail kind of assumption. So if you take your underlying distribution that has mean mu, and you condition on the complement of some event of probability epsilon, so you condition on a 1 minus epsilon probability event, you will move the mean only by some distance sigma. And this is a 1D picture, but you can imagine that this makes sense in D dimensions. So both of these assumptions will enable you to get error that's smaller than root epsilon, but no polynomial time algorithms are known which can exploit either of these assumptions to get error better than root epsilon, unless you make even stronger assumptions like Gaussianness or something introduced last year called certifiable bounded moments. So in this work, we were studying whether or not you should be able to beat root epsilon error in polynomial time from these assumptions, and our main results are reductions from small set expansion and a strengthened variant of it, which suggests that error little o of root epsilon is hard under these assumptions. Hard meaning hard for polynomial time algorithms. And as I said, some algorithms are known under even stronger assumptions that beat this root epsilon error. So we're really trying to understand where does the boundary lie in terms of the space of assumptions between where you can beat root epsilon and not. Let me mention just a couple of prior works in a similar space. In particular, these first two are about hardness of robust learning. So Hart and Moitra have given some reductions from small set expansion in the context of robust learning. They show some hardness of robustly learning subspaces. Unlike their work, ours manages in our reductions to show hardness for learning under niceness assumptions, right? We have these niceness assumptions that we need to show hardness under. That's like the bounded moments assumption. Whereas these older works on reductions from SSE in the context of robust statistics don't manage to show hardness under niceness assumptions. We've also seen some results by Dike, Nicholas, Kane, Stewart on statistical query hardness in robust statistics. This would also be an appealing route to show that you can't beat error order root epsilon, but it actually cannot work in this situation because there are algorithms for these problems which make a small number of statistical queries. Okay, so you're not going to be able to show computational hardness by proving statistical query lower bounds. And finally, let me mention another work by a whole bunch of authors from Fox 2012. This is not related to robust statistics, but it does provide some reductions from small set expansion, which mathematically inspire ours. Okay, so let me tell you about our results. Remember that under these two assumptions, bounded moments and resilience, getting error order of root epsilon is possible information theoretically. So we have two flavors of results. The first flavor of results is not about robust mean estimation directly. Instead, it's about the question of deciding whether or not these properties apply to the empirical distribution of a list of points in RD. Okay? And now this is actually still a reasonable, this kind of hardness is reasonable evidence that, that robust mean estimation could be hard under these assumptions, because all the existing algorithmic paradigms we have for robust mean estimation need to decide analogs of these properties, like they need to decide whether or not the points have bounded covariance in order to achieve this root epsilon guarantee. So these kinds of results, which I'll say in a minute, they are able to suggest that existing algorithmic approaches will not get you error little o root epsilon in polynomial time. So what are the results? First of all, the first result is that if I give you a list of vectors y1 to yn in RD, it's small set expansion hard to certify that they have little o of root epsilon comma epsilon resilience. Okay, so this is the amount of resilience that would get you information theoretically little o of root epsilon error. And it's also SSE hard to certify if their empirical distribution has bounded teeth moments for any constant t, where actually we make a slightly more subtle theorem statement. We show that it's hard to decide even if they have sub-Gaussian teeth moments, moments that are growing at a sub-Gaussian rate. And the second theorem is a quantitative refinement of one of the main theorems from this paper from 2012. But what if you want to attack hardness of robust mean estimation directly? So we are able to show under a strengthened version of small set expansion that it's SSE hard. We're calling this strengthening unique SSE. It's unique SSE hard to robustly estimate the mean of a little o root epsilon resilient distribution to error little o of root epsilon. In this context, the best efficient algorithm does achieve error almost big O of root epsilon. So what is this assumption? Let me remind you what the small set expansion hypothesis is. Small set expansion hypothesis, which is illustrated in the top line of this figure, says that it's hard to distinguish the following two cases if I give you a graph. In the yes case, there exists some small set of delta n vertices, which is poorly expanding, has expansion like 0.01. Whereas in the no case, every small set of vertices expands well, has expansion like 0.99. In unique SSE, we strengthen the yes case to say that, that this problem is still hard, even if there's only one set of delta n vertices that is poorly expanding, and every other set which is disjoint from it is expanding well. Okay, so let me tell you in 20 seconds the proof idea. The proof needs to take a graph, and it needs to produce a list of vectors such that poorly expanding sets somehow correspond to corruptions in the set of vectors. And what we do, this is a reduction that already appeared in some number of these works below, is we spectrally embed the graph. We take our graph, we embed each vertex into RD according to the high eigenvectors of the graph. And then we can show that actually poorly expanding sets of vertices will have embeddings which form a cloud that's far away from the mean of the rest of the embedding. So they form corrupted sets of vectors. So we gave some evidence from small set expansion that it's might be hard to do robust mean estimation to err a little over root epsilon under bounded moments or resilience assumptions. We introduced this new unique SSE strengthening of the small set expansion hypothesis, which really is crying out for some battle testing. And with that, thanks very much.
I have time for one question while the next speaker sits up. I have a question. So, do you think we can get hardness based on some average case hardness assumptions like planet leak or?
That's a good question. I don't know. I think I'm aware that there have been some efforts to do this, and they're not successful yet, but that doesn't say why we shouldn't be able to do it. It's conceivable that average case assumptions